So I'm going to talk about work done in collaboration with Philippe Brax, who appears to be missing, and Johannes Nola, that's published in JCAP, and it's on the archive. So what I'm going to do is to first talk about why and what doubly coupled bigravity is. And this refers to work that Philippe, Johannes and I did in a previous paper. I'll go through the model and some of the properties of the model, look at the constraints on the model, and then look at what happens with astrophysical sources. And I'm told that this thing should automatically change. Oh, it does. I normally do it manually. Okay, so what's bigravity? Well, we heard about massive gravity last week. Bigravity is where we have two gravitons, with both gravitons coupled to matter, and there's a non-diagonal mass matrix. Why? Well, it seems more natural, to me at least, to have both gravitons coupled rather than having, and dynamical, rather than having one as a reference graviton and the other one dynamical. But others, I believe, disagree. What we have here in our model is a ghost-free massive gravity, and if one diagonalizes the mass matrix, you're left with one massless graviton and one massive graviton. And the parameter here would be, so the mass is of order h0 today. It's a dynamical model, so it could have interesting predictions. In particular, the mass matrix is time dependent, so it could give rise to very interesting predictions in gravitational waves. So what is the model? Well, any massive gravity model is complicated, and I am not going to go through all the technical details. We heard about a lot of technical details last week, and if you weren't here last week, Andrew's notes are online. Bar one page. Okay, so the action consists of three terms. I'm using the Vierbein formalism, and those of us who are mature know about this when we dabble in supergravity. And if you're not mature, it's good for the soul. It's got the Einstein-Hilbert term with the Ricci for the two gravitons, and the Vierbeins E1 and E2. The two Vierbeins satisfy the symmetric condition given here, and we saw this last week. The potential term is written here. These are parameters, coefficients, so two epsilons and three Vierbeins. Four Vierbeins, sorry, I can't count. It's called a senior moment. And a parameter lambda 4, which is on the next page. Finally, there's the coupling to matter. So psi represents an arbitrary matter field, not just fermions. And here, G mu nu is the Jordan metric, and it's described in terms of the metrics that occur buried in this guy. In terms of beta 1, the metric for the first one, beta 2, the metric for the second one, and this cross term with the symmetric tensor y mu nu, written down in terms of Vierbeins. And the scale factor is just m squared, m Planck squared, and m is related to the graviton mass of order h0. So now let's choose a cosmological background. So ds1 squared is scale factor a1 squared, d eta squared plus dx squared. And ds2, a2, the scale factor for the second one, b squared, this is the parameter of the model, d eta squared, dx squared. So the ratio of the two lapse functions are related to the parameter b, and this plays very much a crucial role in the modification of gravity. When we did the analysis of the full cosmology in the first paper, we could see the role of B, and I'll display it later. And as I said, matter couples to the Jordan frame metric with Jordan scale factor in terms of the two scale factors A1 and A2, and beta 1, beta 2. So from that, we can derive the Friedmann equations. There are two of them. Here they are. And just note that here we've got these extra terms coming from the potential terms, but actually there's couplings in the Friedmann equation. So H1 and H2 here are derived from the respective scale factors A1 and A2. And the m's arise from the potential term. Now there's two branches here, and the branch that we choose satisfies B is A2 H2 over A1 H1. This branch is ghost-free, does not have instabilities, and gives rise to sensible cosmology today, and in the radiation and matter eras. She hastens to add.
Is it possible to go to some sort of minimally coupled frame here?
I'm sorry, pardon?
Is it possible to go to some sort of minimally coupled frame here? Well, you want the geodesics?
The geodesics?
Yeah. What you call H is really the H of the metric of which the
yes.
Geodesics, right?
Yeah.
So the one that we measure is related to the one that I hear.
Okay. So when we can now analyze the full cosmology of this system and look at what we actually measure in actually in the CMB. And Sebastian did that yesterday to look at the CMB predictions of this model. So you can do it. And if in our first paper we looked at the radiation matter transitions and the late time cosmology. Hello, Yasha.
Sorry, that's just a very good question. I'm a little confused. This is the dynamical branch that we usually call.
Yes.
If I remember correctly, this one has instability.
Sorry?
This branch has instability.
No, not at the scales we're looking at. No, it does not. No, we did investigate that in our first paper. Okay, so the dynamics at both early and late times in all eras essentially depend on the ratio of the scale factors, and that just and it converges to a constant, which is just given by the two parameters, beta 2 over beta 1. And for most of the development of the universe, B is equal to 1. And B is the only thing that sets aside any, one scale factor to the other. However, when dark energy dominates today, or eventually, B is not equal to 1, and then the ratio of the two scale factors goes to something very different. So we've looked at the development of B, and with a bit of luck it's on the next transparency, but it's not. So this is just what I've already said. For most of the evolution of the universe, B is 1. In between eras, it deviates from 1. Actually, going from radiation to matter, there's a brief time when it's not equal to 1, and when dark energy dominates, it's not equal to 1. And when B is different from 1, we have non-standard gravitational wave propagation. So here's the diagram I said was going to appear last. This is the behavior of B as a function of log A. So here it's not equal to 1, briefly. So the potential term induces a mass term for the gravitons with this mass matrix. This is the mass parameter, and here we've just got, well, it's a matrix, right? If I sit down and diagonalise it, I get one massless, one massive, but there's off-diagonal terms here. It connects the two gravitons. So because this actually evolves in time, as the universe develops, there's a mixing between the two gravitons, which could be observed as birefringence when B is not equal to 1. So now let's look at the coupling equations for the evolution of the gravitons. I've written them down here. Mass term for one, mass term for the other, mixed non-off-diagonal terms, and B is appearing down here. So what does this do? Well, for B not equal to unity, it could have interesting signals in gravitational waves. It does have interesting signals. Matter couples, as I said, to the Jordan frame metric, and we can then look at the evolution of gravitational waves with the Jordan frame metric and see how we get deviations from standard GR. So, for example, I thought my talk was a little dry, so I put a diagram in. What happens with binary pulsars? I believe this is a famous pulsar. We can sit down and analyse what happens with binary pulsars compared to GR. So the rate of loss of energy is that of GR times the Jordan frame metric. The parameters of the model, there's the B there, and A tilde is related to AJ, the Jordan frame scale factor, but rather than writing it like this as AJ, beta 1, A1, beta 2, A2, there's a B here. So where I forget which, there I am. Good, I'm on that right slide. So the only deviations we get from GR is when B is not equal to 1, from there and there. Yeah. And B is not equal to 1 in the present universe. We know the energy loss from binary pulsars. This is constrained. So this tells us that this set of parameters, these guys, are constrained to be between 1 and 0.995. So B, little b, is constrained at order 10 to the minus 3 level, which means there are small deviations from GR at that level, or there could be.
Sorry, also just to comment. Here you are considering pulsars as point particles that are orbiting.
Yeah.
In principle, they also should. You consider them as what they are, like extended objects.
Yeah, I mean, we just compared the standard calculation for the.
Very strong, right? So, in principle, the system is not going to be covered. You have extra degrees of freedom, so even
Okay.
radiation.
Yeah. Yes, I know. In principle, there's scalar radiation. Yes, of course. We compared the standard GR calculation with massive gravity. I agree that there could be scalar radiation, but we did the simplest thing to constrain the parameters of the theory.
Yeah, but that's approximate. Things can go. Maybe you get the ballpark, but if you want to be very precise with parameters, I think you have to do something more.
Okay.
It is at least this effect. It is the minimum.
Yeah.
Okay, so let me continue. If we consider the propagation of gravitational waves, so let's consider an initial localized source and approximate the waves as plane waves. So these are the propagation equations for gravitons with eigenmodes here, H plus H minus, and eigenfrequencies omega plus omega minus. And there they are, they're differing there with a B factor. And the M's come from the mass matrix. And it gives us two eigenmodes, where H plus and H minus are related to the H1, H2 by a factor C, which depends on the mass matrix and the parameter B. A characteristic wave number, which depends on B and the mass matrix. And omega plus minus omega minus is related to B minus 1. So we can look at the Jordan frame H and look at the emission. Horribly technical equation. You won't absorb it. I hope you can see it actually. It looked okay on my computer and I couldn't do it any bigger. So they've got B factors here. So this is the waveform of a faraway source when the gravitational waves show birefringence. And when omega plus and omega minus are not equal, but but almost, we can write omega as omega plus plus omega minus by 2 and delta omega as the difference. Then if this difference is not is small, we can look at the amplitude of the wave, which has a small time-dependent phase shift. And when we sort of do that, we find that the graviton speed depends actually on the parameter B. So the waves propagate with some energy that depends on the graviton speed and the mass matrix. And CT is 1 plus B over 2. So when B is not equal to 1, C is not equal to 1. But the effective speed is highly constrained because B is highly constrained. And people said I should have done a better job in constraining B. Well, we can, if B is less than 1, if C is less than 1, then cosmic rays give off Cherenkov radiation in terms of gravitons, and they lose energy. We can we can constrain the graviton speed, how much less than 1 the graviton speed is, by sitting down and computing the Feynman diagram of Cerenkov radiation. In fact, we don't actually need to do it. Anne Nelson and Guy Moore did it in 2001, and Kimura et al. Did it as well. In terms of our parameters, this just means that 1 minus b is constrained to be 10 to the minus 17 when CT is less than 1. The other limit is CT is superluminal, then gravitons can decay into photons. And here's the two diagrams one needs to consider. At least these are the two leading diagrams of graviton decay. And these were computed by Philippe Clairbarrage and, well, I was a passenger, I think, in a paper that we wrote on Galileons. Now, these two diagrams give us a similar constraint to that of binary pulsars. So there, when graviton speed is greater than 1, B is constrained at the order 10 to the minus 3 level. Okay.
Where do you get this constraint from? From gamma?
Sorry,
How did you get the constraint there? You need to either see that.
Oh, we, I mean, you can just compute these Feynman diagrams, and look at the this is graviton. So this would be the energy loss, and
Energy loss of the gravitational waves.
yeah.
Or see the look for photons.
So then you can you, I've actually forgotten the details. I'm sorry.
If you could do it, but not
Yeah.
today with the LIGO detection, maybe you could do it.
We hadn't LIGO then. Actually, I'm not sure. I'm not actually sure you can do it with LIGO. I think you can do it with the decay in orbits. So what are the prospects? It's all very well having a model. What unique signal does it give? We can't just constrain a parameter and say, here it is. The unique signals that this model does give is it gives birefringence in the gravitational waves. So there is mixing between the two gravitons as they move from the source up there to our detectors here. So if we have a gravitational wave source at some distance d, then we can consider the square of the amplitude and look at the modulation of the signal. So it's in our paper. I've sort of written it down here. It's probably illegible. It is almost, actually. There's a modulation of the signal. So and the spectrum is modulated by a frequency dependence prefactor compared to that of GR. And you might observe in the gravitational wave detector some sort of beats or modulation of the frequency. It's going to be quite hard to detect because you can only detect it when you get sources around 100 milliparsecs and in the nano-Hertz range. So it's not quite a LIGO range yet. However, we do have a prediction for this model. It differs from other massive gravity models, and who knows, it might be detected. So here we have the emission and propagation of gravitational waves in doubly coupled massive gravity. There are deviations from general relativity with a parameter b that's tightly constrained. We might detect gravitational waves, and when b is not equal to 1, which it shouldn't be if our model is correct in the present universe, then the speed of gravitons are going to be different from 1. So if we have multi-messenger signals, we should observe some difference between gravitational waves and the optical signal. And now people are going to ask, do I know about the rumour? Well, I heard it last week, but I have absolutely no details. So I have not sat down on my backside to see what this says. But I suspect somebody in the audience has. I think Lucas has, actually. Anyway, but if we do observe an optical signal with a gravitational wave signal, then from the arrival time of the signals, we can say yes or no. Or B has to be less than some stupid number. And of course, as soon as you start to say B has to be less than 10 to the minus 100 or something, you might as well throw the model out. But at the moment, there's definite predictions with which we can test. Thank you.
Thanks. So I have a comment about the binary pulsar, and is that this computation, I think it worries me more than the other comments, is that it relies on B, and B is a parameter that you're defining on Friedman, Robertson, Walker. So you
Yes.
somehow are assuming that the cosmological solution is the same in the binary pulsar. And I would expect screening or nonlinear effects. Even for ER, I would expect that you cannot detect the cosmic expansion.
No, we
there.
ignored the cosmic expansion when we computed the binary pulsar stuff. But I don't think screening plays much of a role here. But, okay, I mean, I'll take your point. It's a constraint that we need to consider. How does our thing lose energy? And you know, what happens because the gravitational waves do go faster. We knew that anyway when we computed B. So if we find that this is an accurate real prediction, an accurate prediction, or there's something funny happening, yes, of course we've got to sit down and do a better job, but this is a first approximation.